Okay, hello, good afternoon, everybody. Welcome to EOL's seminar. I'm very honored to be able to introduce our visitor and speaker today, Alan Blyth. Let me tell you a little bit about his background for those of you who don't know. In 1982, he got his PhD from the University of Manchester Institute of Science and Technology. His advisor was John Latham. And then he immediately had a research fellowship at the University of Wyoming in Laramie. So he's hopping back and forth across the Atlantic a few times during his career. And that was his first hop. Then he got a position at the New Mexico Institute of Mining and Technology in Socorro, where he started as a research physicist, and then he became a full professor and eventually the chair of the department there. In 2001, he went back to the UK, working at both NCAS and the University of Leeds. And currently he's the director of the Atmospheric Physics Division of NCAS, which is the National Center for Atmospheric Science in the UK. Additionally, he's a professor of atmospheric science at the University of Leeds. Additionally, he's a visiting professor at the University of Edinburgh in Scotland and an affiliate scientist in EOL for the past 2 years. So Alan has been involved in 15 field campaigns studying orographic precipitation and rain formation processes, starting in 1979 with different aircraft observations primarily. His first research flight was in Seacope in Montana, along with Al Cooper and Wayne Sand, and that was in 1981. Alan has also participated in and led numerous field campaigns in New Mexico, Florida, Hawaii, Germany, Antigua, Honiara, Cape Verde, all over the world. And today he's going to talk about one of those field campaigns called COPE, which was in southwest England in 2013. I'm going to turn off the light up here.
Yeah, that'd be great. Thank you very much, Tammy. It's a real pleasure to be here. It's wonderful being an affiliate scientist here. I really enjoy coming to NCAR and working with you. Today, as Tammy said, I'm going to talk about a project that we had down in the southwest of England. We had a project that Tammy was involved in, and Jim also called the Convective Storms Initiation Project, where we looked with a radar only at the convective storms and how they initiated there. But we never did look at the more detailed cloud microphysics and dynamics. So we always had the idea that we would like to study those in a bit more detail, and the southwest of England seemed an ideal place for that. There are a lot of people, a lot of collaborators, and this BAMS paper shows those people. First of all, Hui Huang, who works with me, she's done most of the work here. I've just talking about it and done some of the analysis. But there's a whole host of people involved in the field campaign, as you well know and appreciate. It actually started as a much larger project, and Tammy was involved in that, submitted a proposal, and SPO and EDO, and Jim too, that didn't work out, and the part in Britain didn't work out either with a large grant. But actually, I was down at my neighbour's having a drink, and I came back and I got the email from NERC to say that it had failed at 11:30 at night, which is when they send these notifications out. It's really quite an odd time to do that, you know. Anyway, so the next day I do like the quotations by Winston Churchill, and he said, "Never, ever, 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 ever give up." So we decided to carry on and try and get another project which we were allowed to do. But we called it Microscope, since it wasn't quite the same scale as COPE. The Met Office were able to do some of the flying, and we provided the radar and some ground-based instruments. I'm going to talk today about this case on the 3rd of August. It's a line of convective cells, and those form fairly frequently in this area. This is the southwest of England here, and it's a peninsula area. They form there basically because of colliding sea breeze fronts. So this is what I'm going to talk about, describe the project, and then get right into the results. And there are a few things here, few important results, I think. One, warm rain is really surprisingly important. Multiple thermals or interaction of clouds is crucial to all this, I think, and also there are lots of supercool. We observe lots of supercool raindrops, and I've always thought that they play an important role in the formation and development of ice, and I think that's true here too. So this is what I'm trying to do. This is preliminary. Look at the pathway to the heavy precipitation from the supercool raindrops, including multiple thermals, the Hallett-Mossop process, which produce splinters, and Garoppolo and heavy rain. And then I'll finish with a summary. The motivation, I guess the ultimate goal really is to increase the warning time for flash flooding. That's what we told the people there when we went to talk to them all on the ground. If we had all the follow-through from what we did to improving the model and so on and issuing warnings, if we were all part of that chain, that would be that is the ultimate goal. We would like to improve the prediction of the quantity of convective precipitation, and to do that we want to understand the microphysics and dynamics. It shouldn't be underestimated now that providing observations for model evaluation is quite important. There was a major event in 2004 at Boscastle. Boscastle is choose my words carefully. It's not the right word, but it's an ideal place for a flash flood because there are 3 rivers going into and steep valleys and so on. But even with that, you obviously have to have this line of precipitation sitting over there for a significant period of time. It is really the perfect storm. The chance of that happening in just that location is pretty small. In fact, when we went to talk to the local people when we were telling them about what we were trying to do, they said, "What on earth are you doing that for? We've had our big flood. We'll never get another one in another 200 years." Basically, they weren't interested in what we were trying to do. So the specific objectives of our project we were going to look at the boundary layer processes, and we did manage a bit that led to the development and persistence of the convective cloud. Mainly we were interested in the cloud physical processes, the cloud microphysics, all the way from aerosols to the intense precipitation, the dynamics as much as we could with our resources, and I'm particularly interested in the interaction between the microphysics and cloud dynamics. We had a much better map with a lot more facilities on it, but in this project we had one radar at this place called Davistow. This is where the Met Office is. The blue circles are the Met Office network radars. Some of them were out of action for a while because they were upgrading them to dual polarization, which is terrible timing. There's a big radar at Chilbolton with a big dish. It does extend out into the area there, and there are other test radars. I've mentioned this Camborne, where there are sounding sites. We did release radio sondes at Davidstow as well. And there were a few more ground-based instruments. Oops, sorry. This is the radar. It's a Celex Germatronic. I say it's modified. Used to looking at the Chilbolton radar with a 25-meter dish, and the one they had with the radome on it was, pretty small. We wanted it just a little bit bigger to have a 1 degree beam width. So the radome doesn't fit on that. And, so it has been modified just for that purpose. It's X-band 3 centimeter, 9.375 gigahertz Doppler dual polarization. It turns pretty quickly, but obviously you can't turn as fast as that if you for some of the processing. In case I forget to mention, we did complete 360-degree turns. This was brand new for us, and the software is quite complicated. We weren't able to do RHIs, and anyway, there were long lines, and we weren't able to even do sectors, so we just went all the way around. So the RHIs I will show will be reconstructed. So this is it on this moor here, which is, believe it or not, Cornwall. I mean, you'd think Britain would be civilized. It was one of the worst places to operate from. It's much easier in Cape Verde, actually. So we had to tow it onto this location every time, every day basically, and set it all up and start it. It's in the middle of a moor on an airfield, a disused airfield, World War II airfield. A perfect location for a radar, except there's no power and there's no internet, and the local town people, or at least the kids in the local town, like to come up to this moor and fire their air pistols. So we didn't like to leave it there overnight. We operated an aerosol instruments in this container here at a local museum. As always, we had a fantastic person on the ground that was a can-do kind of person that runs the local museum there. He was a wonderful man, Steve. He was actually willing to lift our radar onto a control tower. We weren't very happy with that, but he would do anything to help us. Those kind of people, as you know, are fantastic. So these are the instruments inside the aerosol container, an AMS, SMPS. This one was on the aircraft, actually, so that wasn't not there. We measured CCN, and there were also filters measured. We had actually 3 research aircraft in the project, but I'll only talk about data from these 2, which you're sure familiar with. This is BA 146, and the cloud probes are on these pods here on either wing. The Wyoming Kinger with the radar and LiDAR operating with 2DC, 2DP, cloud probe, CDP. The 146 had 2DS, CAPS probe, SIP, and all the usual microphysics probes, CPI, not the 3V CPI, just the normal CPI. We designed the flight plans like this. It's hard to see from the back, I know. Basically, the 146 started below cloud and measured the aerosols and then went up into cloud. The Wyoming Kinger would be at the top, going through the tops of the cloud, looking down with the radar. We thought this would be a good plan, but to try and maximize the coverage of the clouds. But to be honest, there were so many clouds that it was difficult, and so few hours really, that it was difficult to be in the right place at the right time, as I know you are quite aware. Here's the sounding for the 3rd of August. This is without the lifting from the convergence line. There's a capping inversion here. The clouds would get up to around 6 kilometers at maximum. So they weren't particularly deep. I showed you the radar diagram of the line of clouds. Just doing a very rough PDF of the precipitation rate, calculated from the radar, just roughly. looking at the clouds in the line versus isolated clouds, and there were lots of those around, the precipitation rate was generally much greater within the line. And that was an interesting thing that we want to look at, to try and explain that result. You probably know that these, maybe not, the convergence lines in this region form as a result of this sea breeze colliding with the prevailing wind. So this is the prevailing wind here, and the sea breeze forms along, it can form on any of the coasts, but in this instance it formed on the north coast and moved inwards and then stayed stationary. It depends on the prevailing wind speed and how that moves, and why there are two is uncertain, but there are. This one was the most intense one. There are outflows and everything. And this is a reconstructed RHI across the line, with this presumably being the sloping updraft. And note it does maybe go up to 3 kilometers. So this is a wind going towards the radar, and this less so. So the relative velocity is up and over. I always thought it would just converge and move upwards. So this is the radar versus the Worf model for this case. A couple of time periods. Worf didn't do such a bad job, really. A bit more intense in the northern line. The timing was off a bit. The cells were a bit too. They were about the right intensity. No, this is reflectivity. But as I talked to Greg on Tuesday, the area of lower reflectivity is much smaller than in the observations. These are the details of the Worf run that we used. So this is a reconstructed RHI across the line, and I think what is striking here is that they're sort of interacting closely packed clouds. There's a lot of them, and this is from the Wyoming forward-facing camera, and you can see that there are lots of turrets here. The individual clouds are about 500 meters to a kilometer or so. So in the analysis of the Boscastle, was from the network radar, Brian Golding and Peter Clark and others had a look. They found that the cells started and then just developed into the intense rain, and there was just this one single development, it seemed like. At least that's what they presented. What we find is something completely different to that, or slightly different to that, sorry. Of course, these lines might be different. This was not over Boscastle, and different day and everything else, but still. I put a square around these cells and try to just track them at different times. It's hard to track them because they change shape and everything else, but just looking at going along with the wind speed. So we start here, we can see that it intensifies a bit, and then the intensity decreases, and then here it increases again, whereas in this one decreases. So there's a lot of interaction, growing and decaying and growing again of these cells. And I think this is an important feature of the and doing a time height diagram along that, following it, which is difficult to do and open to interpretation, and definitely not reproducible, Charlie. well, we get this kind of thing, and I'm showing it. This is Z, maximum reflectivity with height and time here, and this is ZDR. And you can see from the ZDR that there are several turrets here, or several periods of growth here, and decay. And as I've shown already, you can see that there are several interacting turrets. And most of you, I think, will appreciate that. It's actually quite hard to find evidence of the growth and decay from the radar. So I guess a likely scenario here is there are thermals with a characteristic size of about, I don't know, 700 meters or so, with a lifetime of maybe 14 minutes, as Al and Paul Lawson found in Hyplex and Seco. Then this plume caused by the convergence line, superimposing these two things, combining them, perhaps thermals initiated by the plume flow, although I'm not sure what the role of this is completely at all, really. Is it acting as a plume? Because that goes into cloud. It is cloud, so is it a consistent thing? I'm not entirely sure. There's I've shown here this picture that Keith Browning drew. You might recognize it from a mesoscale convective system that we observed during CSIP in 2005. It shows a kind of thing similar anyway. This is the an updraft kind of plume, and these thermals are spawned on top of it. Yes.
If I can ask, were there any observations of a cold pool?
Some. We're not entirely sure yet, but yeah, I know. The model says there are some, but that's different. We haven't really. We had a Doppler LiDAR that looked, so we've been looking, but we don't have any really good evidence of it. So, one of the surprises of the project actually was the importance of warm rain. This is a different case, but I wanted to show it because this is just warm rain, and it's heavy precipitation from shallow clouds. Here's the reconstructed RHI for these clouds, and the 0 degree level is here. I guess it's possible that there was some ice, perhaps, but flying through it, we didn't find any at all, and a lot of them were lower than that. And reflectivities of 55 dBz or greater. Now, this is England, remember, it's not Hawaii, and we were extremely surprised about this. Everything that we'd seen so far before that were 30 dBz or so. And actually, to be honest, we thought the radar was broken. Well, we calibrated it at the end, and that is the real result. So that's relevant for the warm rain in itself, I think, which is an important process in flash flooding, even in southern England. I don't know about Scotland actually, but also because of the role of the supercooled raindrops. This is reflectivity. This isn't the best example. I'll show some more others later. The 0 degree level, which I should have drawn on here, was here. This is ZDR, so you can see there's a positive ZDR signal here. This was fairly common on this day and other days, that there were these columns of supercooled raindrops. So the fourth thing I wanted to talk about, and the rest of the talk really is about the this possible pathway. So here are some SID plots. This is the BA 146 track through this cloud. It's not at the same altitude. If I showed it at the aircraft altitude, there would be nothing there, because the radar operator, that's me, was pretty useless. And well, you know, I mean, these lines go forever, so it's you have to compromise, and unfortunately we didn't get it right, so it's cut off here. It is not the best, really. But anyway, so the aircraft was above where the radar saw. This is Z and the ZDR. So we can see here, again, a column of supercooled raindrops. And this is the aircraft pass. This is from a paper that's already published by Johnny Taylor et al. In ACP. Concentration of a number of things from the 2DS probe. The CDP is in this lighter gray. The dark color is the liquid water content on this scale. The red is what from the 2DS is determined as round particles, and the blue is determined as ice particles. So in this, and this is at -5 degrees Celsius. And that was a new turret. Oh, they were pretty close. They weren't at cloud top, but they were in the updraft. Now, this is the problem. Why we want to do some studies in maybe New Mexico. But this, so this is the updraft here, and it doesn't have any evidence of ice there. No, whereas in the downdraft, there is some ice and more evidence of these round particles. This is in the updraft region, and this is in the downdraft region. The top ones are what the software determined as round particles, and the bottom two panels are what determined as irregulars. So this is a downdraft here. So there are some graupel particles, and there are some drops present. This is a scale across here, 1.2 millimeters. Not particularly large, but so at -5 in this updraft and downdraft region, there's a mix of the particles. The Wyoming King Air was at the top of the cloud, and this is a forward camera of the cloud. The blue is just from the 2DP, and need to do more analysis on this, but less than 5 per liter, 300 per cubic centimeter of cloud droplets. Higher liquid water contents, 3 grams per cubic meter. It's not a very strong updraft at cloud top of 5 meters per second. So only 5 per liter or so of ice particles, and here they are. Now the temperature was -12, and it seems like these are either liquid or at least recently frozen, and a mix of graupel. This is only 800 microns across here. So, and the 2DP, it's hard to tell what those really are, but mainly graupel particles. I think on the next pass, the reflectivity went up just a little bit. This is an anomalous here, but there's still a column of supercooled drops present. The aircraft ascended to -7. There's a stronger updraft. Still some round particles, a little bit more ice, maybe 30 or so per liter. The cloud top is -13. The Wyoming King Air was at the top of that particular turret, although you can see it's quite messy. Strong updraft this time, or stronger updraft of 10 meters per second. High concentration, 400 or so per cubic centimeter. Very little ice in this updraft, -12 near cloud top. Still very little ice in this region too. So the updraft's gone through the Hallett-Mossop zone. It's ascended up to this level, and there's still very little ice. There's a bit more ice in this turbulent region here, which is a different turret, but still less than 5 per litre. It's a frustrating story trying to put all this together because, as I said, the aircraft's always not in quite the right place. There's still some what look like either recently frozen or liquid drops at -12, which is interesting. That pass of 146 wasn't through the strongest core, so here this is a continuation of what happened. The aircraft then went to the side of the main core, so here's the reflectivity and the ZDR. Quite a strong signal of ZDR, 3 dB. It's hard to tell. That is 3 kilometers. No, sorry, that's 3 kilometers there. So this is a column of supercooled liquid. The reflectivity gets up to about 55 or even stronger reflectivity. Presumably, this is all due to liquid. Now you see from here and to here that the cell decays a bit and then grows again. So maybe this is some evidence of the multiple thermal nature of it. Then the aircraft made another pass in a different cloud, slightly higher, at -12 degrees Celsius with the cloud top at -16. This is the updraft region here. This is the plot of the vertical wind speed here, going up to about 10 meters per second maximum. Less in the middle region, and almost zero here, just a turbulent region, and that's where the ice's concentration, which is in blue here, is a maximum. The black is the liquid water content. The grey is the concentration of cloud droplets, which has dropped to 100 per cubic centimeter here. But still not an awful lot of ice, at least in the updraft region, which is surprising. Unfortunately, this is about the only evidence we have of there being any columns. Johnny Taylor and the others at Manchester suggest that these columns have been transported upwards to that level in the small updraft region. So it's a bit inconclusive, all this, but well, we'll keep going. And actually, there's still a lot of thinking to do and analysis to do on it. And actually, that pass was this period here. So this is reflectivity here and the ZDR signal. This is 8 minutes earlier, or nearly 10 minutes earlier, 4.5 minutes earlier for that cloud that they made where they made the pass. They were up at this level here, so you can see that there's a lot going on. It's going to be awfully hard to interpret that aircraft pass. One of the main messages, though, is that there are quite a number of supercool raindrops. So when you can't find the results from the measurements, resort to modeling. And I did a few calculations. It's quite a while ago now. I was going to try and do them again, do some sensitivity studies. So we released a spectrum of ice particles at a particular level, and then imposed some dynamics on it. Just a very simple dynamics model, and looked at the growth of the ice particles in detail. It's got quite sophisticated cloud microphysics based on a bit on Al's Grapple model and some results of Andy Hamesfield. I think he's at home listening. The terminal velocities and so on. So I built this, designed this little model. you can change where you release the particles and so on if you really wanted to do that. There are much more sophisticated models around now, of course. What this is showing is these regions here are the updraft, and then there's a gap, and then there's another updraft and a gap and another updraft. This is all very simple, imitating multiple thermals in New Mexico, where they grow over the mountain in a linear fashion. And these represent the trajectories of particles. And when they get into the Hallett-Mossop zone, which is here, they release splinters, so there are many more particles produced. So I think this indicates very nicely the effect of these particles falling into a new thermal. And that's the message here. So this region here has more liquid water content in it. So as the particles fall into this, the Graupel and the ice particles, then more particles are Hallett-Mossop splinters are produced. This is a multiplication fraction with time, and even multiplying an initial fraction by 10 or 50 or so gets you to quite a reasonable number of particles. It's quite a long time to get higher, and the whole line system didn't last that long. I think you get the picture. And so we did this with a more sophisticated model, at least more sophisticated in terms of dynamics. It's a model called Mach3, which is an axisymmetric model with detailed microphysics in it. So the dotted line here, which is this dotted line here, is a single thermal. We also imposed a double thermal at 17 minutes, which is the solid dashed line. This one here is a plot of concentration of ice versus time. So you see when you have this double thermal, then you get an awful lot more ice produced. Interesting. This is at 22 minutes. This light grey line, and just as I was showing in the previous slides in the simple model, if you don't get the gap right or don't get the thermal coming at the right time, then you won't get this increase in the concentration of ice. Worf showed that these clouds interacted and produced more ice by doing so. So this is an older cloud and a new one coming through. I know this is in 2-dimension, but we looked at the plan view and so on, so they definitely are interacting here. And at a later time, this cloud is going through the remnants of the other one. There's Graupel particles in here, so this is got more liquid and supercool raindrops in it. So these do interact in Worf quite nicely, actually. This result shows interacting clouds, or this one does. The top one is for a single thermal. There was an example, like I've just shown you, of a double thermal. There's a plot of concentration of ice on the top, a time-height diagram of concentration of ice, and on the right, a concentration of Graupel. This was a single thermal, and this was a double thermal. And just by looking at the scale here, we see slightly more ice and more Graupel in the double thermal. So
were these things electrified then?
No, they weren't. Well, I don't know, actually. They might have been. They certainly weren't enough to produce lightning, but I don't know if they were electrified or not. That's a good question. Probably, slightly.
It seems to have all the ingredients.
Yes, quite. Sorry, I answered no to a question of whether it produced lightning. I was too hasty. You're right. It must have.
Okay.
Yeah.
I don't think there's enough total ice in it.
Oh, is that right?
To do that.
Sorry?
I don't think there's enough total ice in it.
No, maybe not.
Probably was somewhat electrified.
Yeah. So I know we don't have enough observational evidence. It doesn't stop us trying to suggest what's happening. So this is a very bad schematic diagram of what we think is going on. We've still got a lot of analysis to do and thinking to do. There's certainly warm rain, and the question is, are ultragiant aerosols important? I know Jan's listening at home. We think they are. Jan and I have talked about taking the Mocha aircraft and sticking his gun out it and flying down along the peninsula there. There certainly is warm rain and high values of ZDR with low values of reflectivity, suggesting that there are ultragiant aerosols. There certainly are supercool raindrops. The question is, do they freeze first? What's the role of these supercool raindrops? So here they are freezing here. So if the whole thing goes up past the Hallett-Mossop zone without producing much in the first place, then if it's all just one thermal, as Paul Lawson is suggesting, maybe there's something else going on. But you can't just rule out that the possibility that there are going to be multiple thermals in the cloud. It seems like most clouds have them. They're very rare to have just one solid updraft from cloud base all the way up. I'm sure there are examples. Andy's suggested that might be true in iced-tea cases. So then, with the second thermal, these few grapple that you might have produced fall down into the Hallett-Mossop zone, and then the whole thing can take off in the way that Chisnell and Latham suggested, and others since then. So we're suggesting that it's this multiplication of the grapple particles that produces the heavy rain. It's that process that is important for the heavy rain process, and not just the warm rain process on its own. So producing more grapple is the key to the heavy rain, we think. So, in summary, there was a convergence line due to the north coast sea breeze front colliding with the prevailing southwest wind, and it depends, on the local conditions, whether that's stationary over a particular region, and whether there was no flash flood on this day because there was no river catchment underneath, and probably the individual cells were maybe too small or not intense enough. There was this sloping plume that is curious. Deeper thermals are no doubt spawned from that, but what's the role of the sloping plume in itself? There were definitely multiple closely packed clouds along the line, and these cells undergo several stages of growth and decay. And the precipitation rate is greater in the line than in the isolated clouds, we think, due to more grapple. It probably only takes a couple of thermals to do this. There's no evidence that 3 or 4 pulses produces any more precipitation than in these two cases. I wanted to finish just by saying it's nearly 35 years since this. We named our project after this project, which was a fantastic project. Some of the objectives that we had were very similar to the ones that were in COpe. So what progress has been made, what questions remain challenging, and what new measurement strategies are needed. It's interesting to think about that. I've put down some examples. I'm not sure that covers. Well, there's a lot missed off here, but there's been a lot of improvement in models for the warm rain process, but it's still unclear, as we'll tell you, the influence of entrainment and turbulence. And as Jan will tell you, the importance of the ultragiant nuclei is still unclear. There's a lot of progress in understanding the nucleating properties of many, many different materials, but then what's attached to these materials? What's attached to the dust and the bacteria? There's some evidence in Cape Verde that maybe ice nucleates at -3 or something like that, whereas here we didn't seem to get that. so there's still a lot of questions there. And then of course this secondary ice production, the physical process that's actually going on. I mean, Charlie's not going to do these experiments, but we need somebody to do them, I think, and get the rates. The rates are, of course, important for the models. We use parameterizations that were developed in the 70s. Then entrainment and the depletion of the liquid water content. The liquid water content, the high liquid water content cores are key to the production of precipitation and the Hallett-Mossett process. And so they're where everything goes on, really, these cores. So entrainment's important. We've got some physical explanation, but certainly a parameterization is not really there yet at all, and there's still a lot of questions. We don't have a good in-cloud temperature probe on our aircraft. I know you do, but we certainly need to make more measurements with good in-cloud temperature probes. And then, as Hugh was saying on Tuesday, and others, the density of Graupel is a big unknown. Models calculate that. The detailed models can calculate the density of Graupel as these particles go through the cloud, but bin microphysics schemes don't do that necessarily, and it's difficult to measure. And aggregation, melting, etc., etc. So, thank you.
So as Alan mentioned, there are people listening online, so we're going to use the microphone for questions. Yeah, George.
Do you have any thoughts on what sets that scale you mentioned for the convective clouds, the 700, 800 meters? And also, do you think that's typical for England?
I think the depth of the boundary layer probably, but it is quite typical for England. But I don't know what makes them aggregate and become larger systems. We do get mesoscale convective systems there, but and squall lines and so on. But that's probably influenced by fronts, etc. I mean, how do you define when you look at the radar reflectivity? It's much bigger, but looking at the top, it's the individual turrets are 700 meters or so.
So we also said that there were some other clouds around, north or south. Were they much different? I mean, clearly when you get a line, then the entrainment is kind of, limited to just one or two sides. Am I right? In 3D you get entrainment from all edges. Does it make a difference? I mean, certainly for the precipitation, I would argue it probably does.
Yeah, we've thought about that quite. I've got a microphone. We've thought about that quite a bit, and Sonia's looking into that somewhat. And that cloud workshop, I produced that diagram. The surface area is less, isn't it, of the clouds in the line? So it must have an effect. In fact, it's a bit curious when I was looking at the video there. I don't know. The eddies look different, right on the top. Something going on there, I think.
Very nice, Alan. It's kind of neat to think of COPE as being a milestone.
It's a bit frustrating more than
for other people. It would be Toga Core and Gate and things like that, but COPE is a milestone for many people. This idea of the multiple thermal seems to be essential and pretty reasonable that the multiple thermals are involved, as you suggest. Is there a way to observationally track those and come up with a way of kind of
Well, we did in New Mexico, yes.
With the trajectories and that sort of?
You mean observationally?
Yeah, I mean, if you wanted to look at a cloud with radar or models or particle trajectories or some observational method to try to say, well, are these thermals interacting as you suggest? And I mean, your models suggest that.
I think they have to be here, and the radar shows that. I mean, it's difficult because the radar is only picking up when it's well developed into precipitation, but there are definitely pulses there. In New Mexico, it was an awful lot easier because the mountain range, the clouds grew over the mountain range, and you could see by making several passes through the cloud, the updraft would peak and then go down and then peak again. So that kind of thing, and then the radar saw that too. Once the precipitation had developed.
Sure, it's going to be quite affected by things like shear, and so it's.
Yeah, absolutely, and it's more complicated in the line. I didn't mention. I don't think actually I should have that these clouds were moving along the line at about 10 meters per second. So it's not a case that they were on top of each other. They were moving along and interacting that way.
So in principle, you can think about the fact that at the cloud base, when the buoyancy, or slightly above the cloud base, when the buoyancy kind of increases, you can think about the kind of cloud base being the flow below the cloud base being relatively steady, and then the air above, because of the acceleration, kind of, I don't know how to describe it in English, kind of detaching itself, because of the acceleration, and you get those kind of individual bubbles. And
Yeah.
I think if you do high resolution simulation, I would say 20, 30 meters, you should see something.
I know.
We've definitely seen it with Jean-Louis, 20 years ago in 2D, but of course 2D is different than 3D, but we showed something like that in the high resolution.
I was thinking about that too. We've got this new Monk model in the UK, a Met-Office NERC LES model. So we can run at really high resolution. That we're going to try and do that kind of thing. But you're right. I mean, I don't know what the role of that plume is really. Yeah.
Any other questions for Alan? So Alan will be here for another day yet, so feel free to go and talk to him, or you can send him an email anytime as well. So let's thank him one more time.